Okay, so welcome everybody to the ICS Friday seminar. It's my pleasure to introduce our speaker today, Enrique Gaztañaga. Enrique is a professor at the Institute for Space Sciences in Barcelona. And he's been active very much in the field of observational cosmology, but also more fundamental aspects of cosmology recently. So he did his PhD at the University of Barcelona, then did a Fulbright Fellowship at Fermilab in Chicago, was a Marie Curie Fellow in Oxford and professor in Pueblo in Mexico before he moved back to Barcelona in the early 2000s. And he did a lot of contributions to galaxy surveys like the 2D FGRS, the Dark Energy Survey, BOSS survey, and I think DESI and Euclid as well. And is one of the founders of the POW survey. And he's involved in aspects like in data analysis and up to the understanding of the observables, like the connection between the matter field and the galaxy distribution. And over the recent years, he started to work more on the fundamental questions of cosmology, what is driving the expansion, and how this can be all put into one picture. And this is what he will talk about today. So
thank you, Kai.
Go ahead, Enrique. Mm-hmm.
Thank you very much. So you can hear me, right?
Yes, very well.
Okay. Well, so I'm going to talk about this idea of the black hole universe, which has several phases, and I have put this subtitle, or the many phases of nothing, and I'll try to go through that. What I mean by that, and the motivation, of course, is behind this is well established. For almost 100 years, we have been struggling in physics to understand the nature of the quantum world and the combination with gravity. And these two theories have several problems, and the one that concerns us here mostly is the singularity problems in general relativity. So a lot of people in the last 100 years or 50 years, several generations of scientists have been trying to understand this issue, including Einstein, and to see if there is some way to merge these two theories into something that sometimes is called quantum gravity. And as you know, string theory came out of that and everything. And there are very interesting ideas going on here. So one of the issues I want to address is if there is a way to understand these singularities within general relativity, within classical general relativity. And of course, this has also been studied by many other people before, although I'm not going to focus on the historical aspects of this now, but in my paper, I do mention some of these. So one of the issues that worries me is whether it's okay to use the Schwarzschild metric to model a black hole when we know it's a non-physical solution, right? A Schwarzschild metric, as we will see, corresponds to a singular point, a point at a position in space, and this has infinite density. So this is not a physical solution. Nevertheless, we use that all the time. Is this affecting our interpretation of physical black holes? I mean, black holes have been observed, they emit gravitational waves. Does any of the physics that we are doing with black holes depend on that? So this is really one of my driving questions. And I'm going to propose a particular model for the interior of the black hole. And what I have in mind is to learn about this. So this is my driving. And I'm going to give a short introduction to the metric for those that are not so familiar with it. So basically, a metric is a way to measure the distance between events. And the most famous one that everybody's familiar with is Pythagoras' theorem, which is the one behind what we call the Euclid metric, which I have represented here. So basically, the distance, ds, which we sometimes call proper time, between events, in this case, represents really the actual distance between 2 points in a space. is just given by Pythagoras theorem. And the metric, the way it looks, we represent it with, you can represent it with a matrix, which is this identity matrix in this case. And we should be aware that the metric appearance depends on the coordinate system. So appearances are deceiving, and this is a very interesting aspect that will play in my talk. Here I show you more of a spatial metrics. So you've seen this before, probably in Euclidean metric, you have Pythagoras theorem, but if you go to the surface of a sphere, Pythagoras theorem is no longer valid. Or if you go to a parabolic surface, you have different versions of Euclidean theory. And this can be reflected into this metric that I wrote here in polar coordinates, and I represent, because we only have 2 dimensions, r and theta, I represent here an example of Euclidean metric, which is just a flat space. The dashed lines represent geodesics, or the shortest distances between 2 events. And on the left, I show you an example of a singular metric. This is, in fact, is the Schwarzschild metric. And you can see how these dashed lines, you can have some of them that are circular, but typically, if you let yourself go in this metric, you will end up in a singular point at the bottom. That's an example of a singular metric. And this phi that I put here is what is usually called the gravitational potential, because that's what it comes when we do the physics out of this. Okay, so the next step to understand the metric was given by Minkowski, who was a teacher of Albert Einstein in Zurich, precisely. And Minkowski noticed that Einstein's theory of special relativity can be cast into 4-dimensional space. Is a nice way to do that, so that the metric is no longer just spatial, but it has a temporal component. And that temporal component comes with a negative signature. And now basically events are characterized both by space and time. And as you know, the simultaneity of events depends on the observer. And the nice thing about this metric is that this proper time defined with a metric is independent of the observer. So we have an absolute way to measure things. But beware that it's independent of the observer, but it looks very different in different coordinates. And that's usually how we express these things in this matrix form. So this is, for example, the Minkowski metric, which is basically Euclidean metric adding time. This uses a speed of light equal to 1. It's usually used. When you do that, then time and space are similar. They have similar units. Well, same units, in fact. And if you put the Euclidean metric or the Minkowski metric in spherical coordinates, this is what it looks like. It's no longer the identity because you're using spherical coordinates. Okay, the next step is to introduce the well-known Freeman-Lemaitre-Robertson-Walker metric, which in fact is basically almost the same as Minkowski metric. The only thing that this metric has that is different is that space is a stretch by a function of time. Okay, so basically it's like if you have a flat space-time, but you stretch that with a function of time, and you can then define what we call the comoving observer, which is moving with this function of time. And for the comoving observer, the metric pretty much looks like Minkowski. And this is very nice because of what I'm going to mention next about general relativity. So this is why I call, the previous one, this one, the Minkowski, I call empty space version 1. Why? Because there's nothing. We will see that this corresponds to a situation where a space is empty. And in some respect, in a subtle way, the Freeman-Lemaitre-Robertson-Walker metric also represents empty space in some sense, just in this sense that is a stretching of empty space. And it turns out that this is the most general homogeneous anisotropic solution for a metric. So if you just apply the geometry and say, well, what if I want something that is homogeneous and isotropic? The most general metric that you will get will be either Freeman-Lemaitre-Robertson-Walker or a transformation of Freeman-Lemaitre-Robertson-Walker. So this is very nice. This is geometrical. So to do physics, what we need is to look at general relativity, which is the theory of gravity. And this is, as you know, is very well known, but it has a fascinating history, how Einstein dreamed of him falling from the roof, right? And when he did that, he realized that in fact, gravity is geometry. So that these two things are interlinked, and there are different ways to look at the same thing. So basically, this is the core of the equivalent principle, where it says that there is a local freely falling coordinate system in which the equations of motions are that of a free body in flat space. So then we use this very simple equation that the acceleration is 0 to introduce these Christoffel symbols, which are going to connect the metric with the physics. And this is done with this, formally with these Einstein field equations, which they look a bit complicated because of the geometrical nature of the metric. And in fact, these are like, these have two indexes like the metric. And basically what Einstein field equation tell us is that the curvature, so basically the metric that I mentioned before, is determined by the energy content. So if you put some energy content, then you can solve these equations, and these equations will tell you what is the metric. So basically, this relates a space geometry with the physics or the energy content that you put. And in the top equation, you have the action. So basically, in the action, you have a term that corresponds to this geometry, the R term. And then you have this Lagrangian, which just corresponds to the matter. So if you know the Lagrangian of the system, you can take this derivative of the Lagrangian, and then you get this energy momentum tensor, and then you solve these equations. So in principle, it's very simple, very nice, very elegant. But it's usually difficult to solve in many cases. So let me show you one example where this is very easy to solve. This is the case where we have the Lagrangian, it corresponds just to a scalar field. So if you have a scalar field, a classical scalar field, you have a kinetical L will be the sum of the kinetical energy minus the potential energy. The potential energy will be given by some curve. I put an example down there. This example is just the superposition of 3 different plane waves. That represents the potential of the scalar field. And then basically the T mu nu, the energy momentum, can be estimated by taking this derivative. And when you do that, you get something that looks very similar to what we call a perfect fluid. You have there the T mu nu for a perfect fluid, basically depends on the density and the pressure of the fluid. And in the equivalent for the scalar field is just that the density is the sum of the kinetical energy plus the potential energy, and the pressure is the difference between the kinetical energy and the potential energy. So a very interesting solution is what happens if your system is trapped into a vacuum, okay? So you can see here, these red dots are false vacuums, and then the blue dot will be the true vacuum. So whether it's a false vacuum or a true vacuum, we say that the system is trapped there when basically the system does not have any kinetical energy or lost the kinetical energy, and all the energy is in form of potential energy, okay? So if we put the kinetical energy to 0, then you have that the pressure equals minus the density, and the density is constant and it is equal to the potential of the field, okay? This is one example. It's a very interesting example because it's a bit not like regular matter in the sense that you have negative pressure. But it's very well understood. It's classical physics. There's nothing magic about that. Some people call this dark energy or quintessence or things like that, but it's just basically a very classical example and simple example to solve Einstein field equations. Okay. So now we can solve the Freeman metric equation that we put before, that metric, which is the most general solution for a homogeneous and symmetric field or space. And then we add that with this perfect fluid equation here. If you put the two things together, then you can actually solve Einstein field equations. And these are the famous equations of the Hubble expansion, right? So you have here the Hubble law, depends on how much matter, radiation, curvature, and this omega lambda. The omega lambda comes from this lambda that appears here in the action. You have this lambda term, which is basically just a constant that you put here by hand if you want. Is a law by the symmetries of the problem. So it's also there in Einstein field equations, and it has a very interesting history, as you probably know. And I just want to mention that this lambda term is basically degenerate with this V term, with this vacuum term, right? So a false vacuum or a true vacuum gives you a constant density, and that's equivalent to a cosmological constant. So then you have that the expansion rate depends on how much matter there is, how much radiation there is, whether there is curvature, and how much is this effective cosmological constant, which is the sum of this fundamental constant that we can put, and also having some vacuum. And I call this rho lambda. You see vacuum plus lambda. Very good, everybody knows that. And also everybody knows that the universe is accelerating. So A dot over A is positive. And if you look at this equation here, this is telling us that the effective lambda is dominating the current expansion of the universe, okay? So what this means in terms of the metric, and this is not, maybe it's not so much stressed many times by cosmologists, it means that we live inside a trapped surface, okay? So we can never cross this distance that corresponds to 1 over h lambda. And h lambda is just the lambda that corresponds, the h that corresponds to a universe dominated by omega lambda. So as the universe expands, all these terms dilute because they go like I to the minus 3, I to the minus 4, I to the minus 2. They dilute, and we end up with a universe that is dominated by lambda. And that universe is inside a trapped surface. So you can define a physical scale that we will never cross. There are no signals that can go out from inside to the outside. The other thing I want to mention is that the next thing that we do, and we have been doing in the last maybe 50 years, is perturbation theory. So we perturb this Freeman-Lemaitre-Robertson-Walker metric with a gravitational potential, and then we explore how a structure grows within those perturbations. And one such structure is going to be a black hole. So a black hole is a perturbation within the Freeman-Lemaitre-Robertson-Walker metric. And basically, this is a metric that what you have here in the bottom, it could very well correspond to the metric of a galaxy or the metric of a black hole in an expanding universe. This is well known, and this is what we do to make all the calculations of the CMB, the large scale structure, barrier acoustic oscillations, etc. Okay, so this is the mystery that we have now. We have that our universe is inside a trapped surface. And the question is, what is outside? Okay, this question is not usually asked, but this is a legitimate question. What is outside this trapped surface? Okay, so let me now do empty space version 3. So the version 1 was Minkowski, right, that we saw before. The version 2, I call version 2 this false vacuum that we saw here. sorry, the false vacuum is this one. I call this empty space version 2. Why? Because the system is trapped into the ground state. And that's what we call usually vacuum in physics, okay? There is no kinetical energy. So that's a false vacuum. Sorry, that's an empty space version 2. Empty space version 3 is the famous Schwarzschild metric. And in fact, as you might know, Schwarzschild was the first one to solve Einstein field equations. Einstein didn't even know that they could be solved. And Schwarzschild, while he was in the trenches of Russia fighting World War II, he wrote a letter to Einstein saying that he found this solution. And this is a very, very simple solution. So if you write a most general metric for a system that has spherical symmetry, as shown here, and you just put that the density is 0 and the pressure is 0, so empty space. Then you do find a solution, and here empty space means also putting lambda 0 and v 0, so nothing. Nevertheless, even if you put nothing, you still have a solution that is not Minkowski, but appears with an integration constant that we identify with the mass of a point, okay? So this is a singular solution where there is one constant of integration that if you just do the Newtonian limit, you can identify with the mass of a point at r equals 0, okay? And this is the famous Schwarzschild metric for a black hole. So I just recast here the same equations, but using this gravitational potential, which I like better. So you have here the most general spherical symmetric metric that you can imagine with two gravitational potentials, psi and phi. And if you put that the density is 0, this P star and rho star is the regular matter, but you can also have, in this case, a cosmological constant or vacuum energy as long as the effective cosmological constant is 0. So rho lambda is 0, but you can still have a false vacuum or lambda. They just have to compensate each other. And in this case, the solution for the metric is that the two gravitational metrics are the same. And the metric that you get is exactly Newtonian potential. And that metric is represented here in polar coordinates, and basically is a singular event. And this geodesics goes to 0, to r equals 0, where there is an infinite density localizing one point of mass m. Another interesting thing about this metric that shows that it's not very physical is that on very large scales, it reproduces Minkowski metric, which is good because you want to have asymptotic freedom when you go to infinite. But when you cross this event horizon, the metric signature changes sign, which is totally unphysical. And I think it reflects the fact that you have a singularity inside. Of course, you can change coordinates using this singular metric and present this in different ways. But I think the proper frame that becomes Minkowski at larger scale is a very good frame and shows that there are some issues with this. So this is the metric that we use all the time to interpret black holes. And I just want to insist that this is one of the main problems of general relativity. It's singular and it's also non-physical because a point cannot have a mass, okay? This was, Newton noticed that, and this is why it took him 20 years to publish the Principia, because you cannot have a point with a mass. You have to do something better than this. So in the case of empty space version 3, we have a mass in a point, and then the real question is what is inside? What is inside this event horizon? So one nice thing that I didn't insist into is that there is a scale that corresponds to when the potential becomes 0 is 2gm over r equals 1, where you have a trapped surface. What it means is that if something is inside this event horizon, it can never go out, okay? There are no signals going out. This is well known, and this is why it's called the black hole, okay? So We don't know, we cannot see what is inside because nothing can come out, but we know it cannot be a singular point, okay? So what is inside? So let me go to empty space version 4, which in fact is going to be the same as version 2, which is called the Sitter metric. And sometimes this is called dark energy. So basically, if you write the most general spherical symmetric metric like before, but instead of putting P and rho to 0, we put also n to 0. But we allow for this lambda term or effective lambda, which can correspond to this vacuum energy or a false vacuum, to be different from 0. What you get for the potential is this other metric, which is very similar to the Schwarzschild metric, but you see the R is reversed. So you have the reverse scaling, and also it goes a square. And this also corresponds to a trap surface. So basically, if you are here in R less than R lambda, you are trapped. You remember that this is very similar to what happened in the Freeman-Lemaitre-Robertson-Walker metric. So if you are inside this 1/h, then signals cannot go out and you are trapped. But nevertheless, if you are outside, then you will see another singularity, because at infinity, this metric goes to become singular, okay? So basically, it's very similar to the Schwarzschild metric, but it's somehow reversed. The singularity appears at infinity. It also has an event horizon. So let me now go straight to the main of the topic of the talk, which is this empty space version 5, which is you can think that this is the most, you can look at this in different ways. One way is, okay, what is the GR solution for this false vacuum that I mentioned before, right? When you have that the system is trapped into a vacuum, but this false vacuum, right? So what you will have in this situation is that you could have a region of space that is trapped in a false vacuum, and then the rest of the space could be in a different lower vacuum or in a true vacuum, okay? So if you have this situation, we can still try to solve Einstein field equations. And in fact, these are the two equations, where there are three. Basically, the first one, which is phi equal psi equal that integral, is one of the field equations. And the other ones are basically consistent with energy conservation, which is this derivative of rho with respect to t equals the derivative of phi with respect to t, and then the derivative of p with respect to r equals to the derivative of c with respect to r. These are the equations. And you can see that when p equals minus rho, which is the situation for a false vacuum, the energy conservation tells you that the density and the pressure has to be constant as a function of space and as a function of time, okay? And that gives you this, the Sitter metric that we found before. So that is what gives you that metric here, okay? But if you look at these equations of energy conservation, you will see that at the event horizon, which corresponds to 2 phi equals minus 1, at that position, then this becomes singular. Okay, so you have a discontinuity in the density and the pressure at that point. And this allows you to think about this solution where the pressure and density is constant everywhere, but it changes value at the event horizon. Okay, it's constant one way or the other, and this represents the situation of a false vacuum solution. So it turns out, and I'm going to argue about this, that this is a solution for Einstein field equation, and it corresponds to this situation where the outside is a black hole with a Schwarzschild metric, and the inside is the Sitter metric, which, remember, was trapped into an event horizon. So we just identify the two event horizons, and that provides a solution to Einstein's field equation. So basically, this is remind you of the problem with differential equations, that when you find one solution, you can combine two solutions to find a new one. Okay, is this, I'm going to then go more in detail about that, whether this is proper or not. But already here, we can see, because of this singularity at the event horizon, that that's something that you can actually do. And so this is the solution. So we have a metric that looks like that. The potential looks like this, is Schwarzschild outside, de Sitter inside, and the density changes inside and outside and corresponds to a false vacuum. So this is how it looks like in terms of the metric. So basically, a Schwarzschild metric looks singular, the Sitter metric looks singular, but if you join these two metrics by the event horizon, then is no singular anymore, okay? And that's what I call the false vacuum black hole, which is one of the types of the black hole universes that I want to introduce, okay? So this is, the question was, what is inside? Well, inside is a false vacuum. That's the answer given by this solution. So another version of empty space, version 4, which was the version of the Sitter, turns out to be very similar and in fact identical to the Freeman-Lemaitre-Robertson-Walker, which I call version 1A, because it's very similar to Minkowski. And why is that? Well, it turns out that there is this frame duality, which I call, that there is a change of variables that you can do going from comoving coordinates to proper coordinates. So you can actually change from the comoving coordinates of the Freeman-Lemaitre-Robertson-Walker metric to the proper coordinates of the Schwarzschild metric. And when you do this change of coordinates, you convert the Freeman-Lemaitre into the Sitter-Lemaitre. This is a Freeman-Robertson-Walker metric with constant age, okay? And this is the transformation. So I show you here, the T is the proper time and tau is the comoving time. So I show you this in a graphical representation. So basically what happens is that the comoving time frees out as you approach this singularity or this trap surface. And that is what, because of this freezing, something that is expanding exponentially in the Freeman-Lemaitre-Robertson-Walker metric looks static in the Sitter metric, because the Sitter metric is static. But these two metrics are exactly the same, okay? That's very interesting, because this is giving us a hint that if the solution was to put inside the Sitter, and it turns out that the Sitter is equivalent to Freeman-Lemaitre-Robertson-Walker, can we put Freeman-Lemaitre-Robertson-Walker instead of the Sitter inside, okay? And this is important because in this solution of empty space where we combine and we do this false vacuum, there is no mass or radiation. There is just this scalar field trapped in a false vacuum. We want to have mass and radiation. And outside, we know we have mass and radiation because there is mass and radiation outside black holes. This is just a perturbative solution to the Freeman equation outside. But inside, it turns out that we can also replace the de Sitter metric by a Freeman-Lemaitre-Robertson-Walker metric. And to do that, you just have to realize that this frame duality is also valid when H is not constant. Okay, and this is what I have found. As far as I know, this is a new result. This is one of the new results I found, that the Freeman-Lemaitre-Robertson-Walker with an arbitrary H, whatever you want to put, is mathematically equivalent to a metric that looks like a spherically symmetric metric, very similar to that of the black hole, which has a singularity exactly at the trap surface that we found in the Freeman-Robertson-Walker metric. This is the change of variables. I put it here. So these are a bit the equations that provide that. And basically, this provides another solution to the black hole. So inside, you have this Freeman-Lemaitre-Robertson-Walker expanding metric, and outside, you have a black hole, which is in fact inside another Freeman-Lemaitre-Robertson-Walker metric. Okay,
so Enrique, can I ask a question?
Yes, please.
Can we go back one slide?
Yes.
Thank you. So I can understand how it would work for the sitter inside, because the sitter has an event horizon.
Yes.
But FRW generically, I mean, it doesn't have an event horizon. So I would expect the discontinuity to not work at the limit between the two. If you do precisely, you know, with theta functions and all, I don't think you can match FRW.
So the discontinuity, so if you have a Freeman universe without lambda,
yeah,
H lambda is 0, and then this goes to infinity. So the Schwarzschild radius goes to infinity, and then you have the regular Freeman. There is no black hole anymore.
Right.
It's only when you have lambda, an effective lambda, then the Freeman-Lemaitre-Robertson-Walker, if you have an effective lambda, is trapped inside an event horizon. Our metric, our universe right now, is trapped inside an event horizon.
Well, it's going to become when it becomes pure lambda. But if you have lambda with something else, so
well, even with lambda with something else, if you send a photon in the future, it will never pass that surface.
Yeah, but do you say that you can write a static metric where you have lambda plus radiation and matter? I don't think you can.
Yeah, this is it. This is what you see in the square. This is on the right, on the square, on the right, in the middle of the slide. You have Freeman-Lemaitre-Robertson-Walker. On the left, you have a metric for a spherically symmetric black hole. Psi can be anything, it's arbitrary. And then the bottom is the sitter. And H is a function of time. That's exactly what this change of variables provides.
And DAK is the standard.
Sorry?
This last DAK squared. This is just the standard spherical.
Yeah, on the left you have it's just proper coordinates.
Yeah, no, it's DA capital K squared. This is just the standard two sphere.
Yeah. This is the reason why I put it this way. This is a bit a formality, okay. Because the Freeman metric, you can also embed the Freeman metric into a non-flat space. So this is just the solid angle. And when you have a non-flat space and you want to do this transformation, you also have to put non-flat in the spherical symmetric metric. Is a formality. Okay. But yes, thanks. That's just omega. So what is inside is the Freeman-Lemaitre metric, okay? And what is outside is also a Freeman-Lemaitre metric, because remember that the black hole is just a perturbation on a Freeman-Lemaitre metric, okay? So basically, let me just jump here. So basically, what we have is that the solution I propose is two Freeman-Lemaitre-Robertson-Walker metric that are linked through an event horizon. And that event horizon is defined from the outside metric, it looks like a black hole. For the inside metric, it just looks like rho lambda, right? It's the same trapped surface. Now, here I go a bit more technical into showing a bit more formally that this is a true solution, okay? And there is a formalist to do that in general relativity. You can take two solutions to general relativity and you can match them together with an hypersurface where they match together. And there is a formalist by Israel where if you manage to show that the two metrics match in this hypersurface where you link them, the junction, and that the external curvature is 0, then this is a new solution to Einstein-Field equation. Usually this doesn't happen. You need to put mass in the surface. And there is a lot of literature about that. People put mass in this surface in order to link these two solutions. And this has become very complicated. But it turns out that in this case, if you choose the hypersurface to be time-line corresponding to a constant comoving radius, I have shown here, this is a demonstration. Well, I didn't show you how to estimate the external curvature, but it's in my paper. You can trust me. It's a very simple calculation. There's no catch here. Then you can show that the junction follows exactly this relation, which is that the potentials of the metric are such that h squared r squared equals r over r, Okay, so that's exactly this here. Is these red circles connect to each other? That's the junction. So you are connecting the two event horizons together, and that provides a solution to Einstein's field equation. So you can look at this a bit more in detail. It turns out that this junction here is not static. It evolves with comoving time. So what happens is that inside the event horizon, which is this dashed line here, you have a metric that is expanding. This junction is expanding. But because from the outside, you only see the event horizon, the final stage of this expansion, I prefer to express the solutions in terms of the event horizon. But in reality, inside, there is an expansion going on where you are tending to this event horizon. And this happens in a finite time in comoving coordinates, but it takes infinite time in proper coordinates to do that. So basically, what is happening inside is that you are here to reach this event horizon. You can see these lines in the top panel reaching the event horizon. It takes infinite time in proper time, but it takes a finite time in comoving time to get there. Okay, so what you have inside a black hole is just an expanding metric that approaches this event horizon. And so black hole universe solutions can be used both for a black hole within our universe, but can also be used to understand our universe as an island universe, which is inside another island universe. Okay, so now this becomes two phenomenologies, one to understand the universe and one to understand black holes. And I just want to mention that if you look at the geodesic equations in general relativity for a general metric, you get this. This is the geodesic equation for the acceleration, G. So it's basically the relativistic version of Poisson equation. And you can see in this equation, which is an exact equation, that you can have negative gravity without the need of negative masses. Okay, the effective lambda, either because of a Paul vacuum or because of lambda, acts like negative gravity. And the black hole universe solution is basically an equilibrium that happens in the event horizon between positive and negative gravity. That's an interpretation of this. And this, in fact, can be used to understand what lambda means. You can then interpret lambda as a boundary. So basically trying to find a solution to Einstein field equations with some boundary. And I call this the zero action principle. I don't want to go through that. But if you are interested in this idea, you can look at this paper where I explain that. And this explains the famous coincidence problem in cosmology, because you can see here that lambda relates to rho. So there is a relation between lambda and rho matter, which is the coincidence between these two things that we see in observations. So is there observational evidence for this black hole universe solution? So I claim that cosmic acceleration is observational evidence, that the coincidence problem is observational evidence, and the fact that we observe black holes is observational evidence, because we shouldn't be able to observe black holes if they were really singular objects. So sure, but is there anything else new? Because basically I have just go back to what we had before, right? There's nothing new here. And I have explored this, and I'm still working on this in this idea of what is new. So here is one example. This is a paper we did with Pablo Fosalva, where what we did is we look at the CMB measurements in the sky, and we fit cosmological models as a function of position in the sky. Okay, so basically you take a very large region of the sky and you feed the lambda CDM model to that region. Well, you feed the baryon acoustic oscillations physics, and then you reconstruct the values of the cosmological parameters as a function of position in the sky. And this is what you find. We find that, for example, for omega lambda varies basically about 25% between some regions of the sky and some other regions of the sky. And in fact, we identify 3 different horizons of different values of cosmological parameters. And it turns out that these values are the same, these regions are the same whether you look at them at one parameter or the other. So what this is saying is that the physics behind the CMB in different parts of the sky is the same. You can fit a model, but the parameters of that model are different. Usually, when the Planck collaboration produce these results, what they give you is the average of these. And in fact, when we average our results, we reproduce the Planck measurements. But there is this locality, there are these horizons defined. And basically, a nice thing is that you can measure the size of these horizons. And the size of these horizons, according to this black hole universe model, are related to the values of the effective lambda. Because remember that if you go back to the model, the size of these horizons depends on the value of omega lambda, on the effective vacuum energy or lambda value. So here we plot the measurements of omega lambda in different regions against the size of the region, either in angular size or in comoving size. The difference between angular size and comoving size is that you need H naught. But H naught is also something we measure. We can also measure H naught. So you see, these plots are more or less independent measurements because psi, the distance, depends on H naught, whereas theta, the angle, does not. And you can see the predictions of the model, of the black hole universe model, is these black lines, and they agree well with these kinds of observations. So this paper is now published in Modeling Notices, and you can check it out there. So that's one evidence for these CMB anomalies. Another way to look at this, which is quite different, is work I'm doing with Benjamin Camacho, a student in our institute, where you can look at the CMB again and estimate what is called the Hausdorff dimension. So basically, it's a way to measure homogeneity such that it's independent of the amplitude of fluctuations. So basically, what you're looking is at the dimensionality of the density as you increase the scale. So this is the Hausdorff dimension. For a homogeneous universe, in the units I put here, you expect this to be 1. It should be 2 if you think about dimensions. But anyway, this is what we measure, the dashed line. The shaded region are error bars, which are, you can trust those error bars. We have done a very careful analysis. The same thing here, Pablo have done a very careful analysis of error bars and found this. This is basically evidence for anisotropy in the universe, which has a very significant evidence. This is not a 3 sigma result. This is very significant deviations from anisotropy. And the same here. So you can see the green line is the lambda CDM prediction. The lambda CDM prediction does not predict a homogeneous universe because basically in that prediction, what happens is that fluctuations outside the horizon falls inside. And this is the way you produce these baryon acoustic oscillations. So you don't recover homogeneity with the lambda CDM universe within the CMB, just because the CMB that we see is too small compared to the universe that is assumed in these predictions. And what we see here is that the universe becomes homogeneous at about 60 degrees, according to this Hausdorff dimension analysis. In fact, this is not something we invented. This is a standard. This has 50 years of history in mathematics to define homogeneity with independent of the amplitude of fluctuations. Okay, this is a geometrical measure of homogeneity. And what we find is that the CMB is not, it is homogeneous, but it's homogeneous on a scale much smaller than predicted by the lambda CDM. And this agrees with this measurement here. These are quite different because one is fitting cosmological parameters, but you still get this 60 degrees scale of homogeneity, which is the same that you get when you do this fractal analysis. So this fractal analysis looks at temperature variations in the sky, whereas this analysis is looking at the whole spectrum on smaller scales. Basically, this is coming from baryon acoustic oscillations at 1 degree scale, whereas this is coming from temperature fluctuations at 60-degree scale. So these are very, very different measurements, almost nothing to do one with the other. And they show the same evidence for these horizons in the black hole universe. So in the future, projects like Euclid is going to map the universe at redshift bigger than 1. And it turns out, if you think about redshift bigger than 1, that the separation between things that are at 180 degrees in the sky, a redshift bigger than 1, is larger than this horizon that I mentioned before, okay? So this is related to this issue that maybe I didn't explain here very well, which is that when we are inside the black hole universe, we can see outside, but the people outside cannot see us, okay? So this is why we can see evidence for what is outside our horizon when we are inside. And I believe that this is what we see when we look at these pictures that I show you here. And I hope that in the future, we will be able to test, of course, if this is, we can also rule out this model for a black hole. That's fine. That will be a way to rule it out. Another way to rule it out is to think about a black hole as an object in our universe. And this goes back to my question at the beginning when I was asking, does the interior of the black hole change the physics of the black hole that we're using to understand black hole formation or gravitational waves? Okay, with another student in the Institute, Carcassona, Mark, we are looking at this idea that when this black hole universe solution accretes matter, it turns out that it doesn't increase its mass. Okay, how can we see that? The way to see that is this duality. So basically what happens in this duality here is that if you put matter into a Freeman-Lemaitre-Robertson-Walker universe, that will soon dilute because you are putting basically some density that is diluting with expansion, okay? This is true even if you put a black hole inside, because a black hole behaves like dark matter, okay? So anything that you feed the black hole with is diluted by the expansion, okay? So, but from the outside observer in proper coordinates, what you see is that you are putting mass into a black hole, and suddenly, after a little while, that mass is diluted, and you get back, basically the mass of the black hole is just this effective lambda term, okay? So what happens then is that that mass that you put into the black hole is emitted in forms of gravitational waves. And I have estimated what is the spectrum of that gravitational waves. I have done here is a very simple calculation. We are now doing a more fancy calculation. But the nice thing about that is that this is something that can be observed with LIGO and Virgo, well, mostly with LIGO. And basically, this predicts that after one of these ring downs where a black hole is merged with another black hole, you should see extra gravitational waves because the black hole will release the mass that it has just eaten, and it will go back to the original mass. Okay, so the summary is that there is this frame duality, and the metric can look very different, so that the Freeman-Lemaitre-Robertson-Walker metric is in fact the metric of a black hole. We cannot separate the space-time, and this is why what you think is homogeneous in one frame, in the comoving frame, it is not homogeneous in some other frame. Black holes cannot be made of regular matter or radiation. Then what is M? Well, we find two exact solutions to general relativity, where M turns out to be the false vacuum or effective lambda term inside this expanding metric that happens inside the black hole universe. The black hole universe is a combination of two known metrics, the Schwarzschild metrics and the Sitter metric, or the Freeman metric plus the Freeman metric. And this is very different from sometimes people, when you hear about these black hole universes, what people do is they connect the Schwarzschild metric with the zeta metrics in the singular point, not in the event horizon. Okay, and this is sometimes is called a wormhole. Okay, that's not what we're doing. That's different, because this is still singular, and also it's nonsense, because you're just mixing two infinities. It doesn't solve any of the infinity problems. So the solutions are good for both black holes and big bangs without singularities. A correction into a black hole does not increase its mass. So this, I think, if this is true, this will change a lot about the models of black hole formation. And we believe it produces gravitational waves. We are trapped inside the black hole universe, and we can look back in the past and see what is outside the black hole universe. And I just want to say that I will be happy to share my draft about this. This draft is sent to monthly notices. I have submitted my draft to arXiv, but arXiv does not like my papers about these topics. I have 4 papers, all published in monthly notices, step 1. But the arXiv says that they don't contain sufficient original or substantive scholarship research. So basically, they reject my preprints. They don't want to. That's why I cannot show you the preprint. You can see an earlier version of this preprint here in the HAL, which sets my papers. I have also sent this new version to HAL, but they take a long time to make them public. So that's why you cannot see it. But if you are more interested about this arXiv, the way arXiv is behaving and why arXiv is doing that, you can go to this site, Dark Cosmos, where I explain that. There is even a letter in Nature about this. So I think this is outrageous. I don't think we should tolerate that, but apparently nobody cares. But that's the situation with preprints. And I finish here. Thank you.
Well, great. Thanks, Enrique. Very interesting talk. Are there questions from the audience? I guess, yeah, if you have a question, just raise your hand. Okay, I see Erm's hand up. So you want to go ahead?
Yeah, thanks, Kai. Thank you very much, Enrique. Very nice talk. I have a question. So about the, let's not about our universe, but about, so you also use this as a model for every black hole as a resolution of the singularity problem, right? Yeah. So, but the problem here I have is, a problem we have with the singularity is that we know from analytical solutions that are well known that this is what happens when a black hole forms, right? We have solutions where you start with just matter, no singularity, and then you see continuously and with coordinates that have no singularities outside, like horizons or whatever, you can see continuously that you're going to end up forming a singularity. And this is just an example of very established results, you know, the singularity theorems of Hawking, Penrose, and all this stuff. So the problem, I could understand that these solutions are idealized, but physically, how can you get there? Because we know from analytical solutions and very strong theorems that we actually do get to singularities, and that's the whole problem with classical GR. So
yeah, this is a good question. So there are, I fully agree with this. Well, let me first mention that these singularity theorems, like for example, the Penrose singularity theorems, exclude implicitly and explicitly scalar fields. They don't apply to scalar fields, okay? So when you have scalar fields and you can have negative, basically you can have negative pressure, you avoid all these singularity theorems. And I think this is key.
The singularity theorems allow any matter that satisfies the weak.
That's right. Negative pressure does not satisfy the weak energy condition. The weak energy condition is pressure bigger than 0. So this is well known. I mean, these singularity theorems go away. But look, I mean, we know there are scalar fields. The Higgs is a scalar field. We know there are scalar fields in physics. And therefore, we know that the universe is expanding in an accelerated way in a consistent, which is totally consistent with effective constant negative density, okay? And that's exactly what the scalar field tells you. So there you are. You have the most simple classical solution to GR, avoids the singularity theorems, and gives you a solution that is non-singular. But having said that, I fully agree with you that the fact that you find a solution doesn't prove that this solution is physical.
Yeah.
You have to show how you get there, how these solutions emerge first. And second, which I didn't mention, you also have to show that that configuration is causal, that you can arrive to that configuration in a causal way. Exactly. So I fully agree that this is important. And I would say that I haven't solved totally this problem, but I do talk about that in my paper. I mention all these issues. I do diagrams of causality. This is something that I haven't fully understand totally, but I think to me, I give plausible ways to get to these solutions. And I think it's worth studying more. It's not worth saying that this is not worth publishing in the archive.
Well,
I think this should be a study. That's my point. I mean, I'm not saying I will be very happy if someone shows me I'm wrong on theoretical basis, or if we don't find these gravitational waves that I predict, that's fine. Then this is ruled out, and maybe we do need quantum gravity. But I think this, I mean, is this new? No, there are many papers that talk about this, something similar, gravity star, baby universes. I think what is new in what I have presented is these two things I mentioned. One is this frame duality. I haven't seen this before. This is a new way to see the Freeman-Lemaitre-Robertson-Walker metric. And I think the other thing that is new is these junction conditions that I show. I think for the first time, I haven't seen this before, that I haven't even seen this for the Sitter space and Schwarzschild, that you can formally create a solution for the Sitter and Schwarzschild following these junction conditions, and you find that there is zero in the junction. There's nothing there. So basically, this image here, I haven't seen this in the literature either. So that's what is new. Whether this is true or not, I agree with you. We need to explore more.
Yeah, and I think what I had in mind as a problem is that essentially what you need is you need your scalar to jump to a false vacuum, right? Discontinuous. Yeah. So the thing is that what we know from the analytical solutions of typical collapse and singularity formation in GR, spherical symmetry, those that we know, is that you really have a smooth accession to this singularity and everything. But what you would need is that as soon as you start forming the black hole horizon and everything, is that inside you really jump. And that is going to be hard. I don't see how this could happen mathematically.
No, it's very simple. Look, here we are. This is trivial. You have a star that is collapsing, okay? Imagine there is a scalar field inside, which we know there are, right? There is a scalar field. Now, if you have a mechanism to, for example, when you have expanding situation, there is this mechanism where you lose kinetical energy, okay, just by damping, okay. You can, if you somehow lose the kinetical energy of that scalar field, and that scalar field got trapped, then immediately you get this kind of solution. The other way it can jump is in a collapse, right? Part of the energy of the collapse could somehow transfer into the scalar field. You need a model for that. I don't have a model for that yet, okay? But if some of the energy goes, then you can jump from a scalar field that is in a true vacuum, you can jump into another one that is not the true vacuum. And you know, if you have a spectrum like this, there are many ways this can happen. So I don't think this is crazy. I think what you have in mind and what most people have in mind exclude these scalar fields, and they just use regular matter when they do that.
So I think a spherically symmetric analytical solution would be crucial to really push this the attraction of this model. Thank you. I mean,
thanks.
Kai, I don't see any other questions. Can I abuse and ask another one, or?
Yes, but then I have a question.
If you have a question, then please, sorry.
Okay, so maybe it's yeah, it's more, well, it's first very naive and more goes. So, can you hear me?
Okay, you got broken somehow.
Yes, okay. I'll try again. So when a star is collapsing, the star before collapse usually has a spin. So you would expect the spin to be conserved after collapse. And could you see then this maybe in like the velocity fields on large scales, maybe in terms of studying redshift space distortions? Or would you expect to be everything, all the motions randomized?
Yeah, I mean, as I said before, I do not have a model to understand a stellar collapse into this, and I think Aurel was right that this is needed to. So my impression is that this black hole universe definitely could be a nice way to get primordial black holes to start with. I'm not sure if the collapse of the star will produce something like that. This is something I haven't shown or proved. And you are right that this introduces other complications. In particular, these simple models are for non-spinning black holes. This will need to be extended to spinning black holes. And this is something I plan to work on just to see how this works. But I mean, basically, this requires much more work. I mean, this is just, to me, this is just a preliminary hint that to me says it's worth extending these models. But I think, you know, more people have to get interested and look into this and try to find, maybe there are two types of black hole. Maybe some primordial black holes are made with this system because it's easy to get into this false vacuum in the early universe. And then when a star collapses, it doesn't get into that, it gets into something else, okay? It could be.
Right. I also noticed that we actually passed the time of the official seminar. So
Okay.
I leave everyone open if people want to leave, but we can, of course, stay longer and discuss more with Enrique for those who are interested, right?
Okay, thank you.
So